The simplest way to show how much uncertainty you have in a measurement is to write it down using the significant figures convention or significant digits convention. In this convention, you write the number down until you come to the estimated digit. That's the last one that you write down. So you never have more than one estimated digit. Take a look at these four measurements. Now mathematically, they would be equal. 3.000 is the same thing as 3, but in science, they're not the same. When I write it down as 3 milliliters, I'm telling you that I don't know it to any better than the nearest milliliter. This might be 2 milliliters, it might be 4 milliliters. If I write it down this way, I'm telling you this is the estimated digit. And this could be 2.999, or it could be 3.001. See, so it makes a big difference where the estimated digit is, and you always know where it is in this convention because it's the last digit that they wrote down. So really what this convention does for us is it gives us a shorthand way to express the uncertainty in the number. If I write down 3 milliliters, I'm telling you that's give or take a milliliter. If I write down 3.0, that's give or take a tenth of a milliliter. 3.00 is give or take 0.01 milliliters. And if I write it down this way, it's give or take 1,000th of a milliliter. So it's a shorthand way of encoding, of communicating the uncertainties. Another thing that the significant figures convention does for us is that it lets us visualize the scale that someone read a measurement off of. So you're supposed to read to 1/10 of the smallest scale division. If you read 3 milliliters, you're telling someone that this is give or take a milliliter. And that's 1/10 of the smallest scale division. So the smallest scale division, the marks, must be 10 times that apart. 10 times 1 milliliter apart is 10 milliliters. How about this one? Give or take a tenth of a milliliter, right? 10 times a tenth is 1 milliliter. That's how far apart the marks must have been on the scale that they read this from. This is give or take 0.01 milliliters. 10 times 0.01 is 0.1. The marks must have been a tenth of a milliliter apart on this graduated cylinder. What about this graduated cylinder? If I give you on a test 3.00 milliliters and I ask you, how far apart were the marks on the scale that they read this from? You're going to look at the estimated digit. It's there. And they read out to 1/10 of the smallest scale division. So the smallest scale division must have been the 100th place. So another way to look at this is if they estimated out to the thousandths, the marks must have been out to the hundredths. If they estimated out to the hundredths, the marks must have been out to the 10th. If they estimated out to the 10th, the marks must have been out to the nearest milliliter. If they estimated out to the nearest milliliter, the marks must have been 10 milliliters apart. So it's going to be useful to us to count how many significant digits we've got in a measurement. And those are all the digits up to and including the estimated digit. So this has 1 digit, this has 2 digits, 3 digits, 4 digits. That seems fairly obvious. But sometimes it's not so easy to count. The way significant figures or significant digits are set up, changing the units on your measurement should not change the number of significant digits you've got. Consider these 3 measurements. Now they're all the same. 12 meters is the same thing as 0.012 kilometers, and that's the same thing as 1200 centimeters. So if you were just counting digits, you might be tempted to say, well, this has 2 significant digits. But when you look at this one, you might be tempted to say, well, there's 4 digits there, but there's not. this is the same measurement as this, so this must only have 2 significant digits. That means that this 0 and this 0 must not be significant digits because they go away when you change to different units. Same thing with these 2 zeros here. They go away when you change centimeters into meters. So all of these only have 2 significant digits. So how can we count significant digits without changing a measurement into all the possible units and seeing whichever one gives us the least digits? Fortunately, there is an easier way. Now, one of the reasons why we want to count significant digits in a measurement is because they tell us about how much precision we can expect. Even though we've got an isolated point here, precision is how they scatter around the mean. We can tell how fine the scale that it came from was, and that implies some things about the precision. Generally, the more significant digits you have, the more precision you have in the measurement.